Welcome to this explainer. Today, we are unraveling a viral internet mystery that, honestly, completely embarrassed the world's most advanced AI models in the summer of 2024. We're going to look under the hood and figure out exactly what went wrong. Okay, let's dive into this. It all starts with a seemingly trivial question that took the internet by storm. How many R's are in the word strawberry? I mean, it's a question a 6-year-old could answer instantly, right? But here's why this really matters. We have these incredibly sophisticated systems capable of passing the bar exam, or, coding entire websites from scratch. Yet this simple little question proved to be absolute kryptonite for state-of-the-art language models.
When you actually contrast the human answer with the AI's response, the results are just baffling. Us humans, we easily identify the 3 R's. Boom, done. But standard large language models like GPT-4o stubbornly, almost comically really, insisted there were only 2. There's no way, right? Well, this bizarre paradox exposes a fundamental perceptual blind spot in how modern AI operates. It tells us that these models aren't actually reading the way we assume they are.
And this brings us to a fantastic insight from Mark Lieberman, highlighted in the research. He notes, you should be wary of trusting the response of any current AI system in tasks involving counting things. This quote perfectly hits the nail on the head. Large language models are probabilistic tools. They're built for pattern matching and text generation. They're absolutely not deterministic calculators. So, to understand why they can't count letters, we have to understand how they actually see text.
So, let's pull back the curtain on the alien vision of AI, because it is truly fascinating. When you or I look at a word, we see a sequence of individual letters. We can mentally isolate the third letter or count specific vowels, no problem. But AI fundamentally sees the world differently. It perceives language through a highly compressed, deeply mathematical lens. The mechanism responsible for this alien vision is called Byte pair encoding, or BPE. It's basically a subword tokenization method. To put it super simply, AI doesn't read letters at all. It reads tokens. BPE works by scanning massive amounts of text and iteratively merging the most frequent pairs of characters together into single numeric codes. This process compresses language, making it highly efficient for the computer to chew through millions of words at lightning speed. And this brilliantly illustrates exactly how BPE works in practice. Take a word like unhappiness. A traditional tokenizer might see one giant word, but BPE fragments it into common subword units. It sees un, happy, and ness. While this makes processing incredibly efficient, it completely masks the individual letters hidden inside those subword chunks. Now let's apply this alien vision to the whole strawberry problem. When we type strawberry, the AI tokenizer slices it into 3 separate chunks: stir, aw, and berry. To the AI, these aren't letters, they are specific numeric IDs. It sees token 496, token 675, and token 15,717. Asking the AI to count the R's is basically like handing you 3 sealed boxes with numbers on the outside and asking you to count the red items inside without opening them. It literally cannot see the 10 individual letters.
So how do we fix this? Let's transition from uncovering the mystery to actually exploring the fix. The first approach the tech industry took was essentially a workaround. Think of it as the calculator versus brain solution. Since the AI's brain inherently lacks the ability to count letters due to that tokenization we just talked about, developers gave the AI access to tools. If it doesn't know the answer inherently, it can just write a little script to find out.
This is achieved through what's called chain-of-thought reasoning, which is a core feature in models like OpenAI's o1. Instead of just blurting out the first token that comes to mind, the AI is trained to hit pause. It creates an internal scratch pad. It recognizes, hey, I'm being asked a character-level question, develops a strategy to systematically break down the token boundaries, tests its logic, and actually corrects its own errors before finally showing you the answer.
As OpenAI researcher Noam Brown explained, O1 is trained with reinforcement learning to think before responding via a private chain of thought. Now this is a crucial distinction. This workaround doesn't actually change how the AI reads tokens at a base level. The tokenizer is exactly the same as before. The AI is simply being rewarded for taking the time to methodically parse out the spelling using logic. And this is exactly why you might see a little thinking animation for several seconds when you're using the newer models.
Now, what's really interesting about this slide is the incredible trade-off this creates.
Just look at the massive jump in performance. On Maths Olympiad questions, accuracy skyrockets from a measly 13% with standard models all the way to 83% with reasoning models. But look at the cost. A response that used to take 3 seconds now takes 30 seconds or more. And the financial cost, it triples. Tool calling and chain of thought are super powerful, but man, they require massive amounts of time and compute.
That brings us to a deeper, wildly curious question explored in a recent arXiv research paper. If standard models struggle so much, how are they ever able to spell words at all? Well, researchers decided to do a kind of brain scan on the deep architecture of the transformer model to see exactly where this spelling knowledge actually lives.
They started by probing the very first layer where tokens enter the model, the token embedding layer. The results were striking. At this initial layer, the AI only really knows the first letter of a token, predicting it with over 80% accuracy. But its knowledge of the second character is remarkably low, and by the time you get to the third character is virtually non-existent. So the token embedding does not store the full spelling of the word at all.
Let's move to and see how this builds across the model's depth. Because if the first layer doesn't know the spelling, where does it happen? Researchers mapped the layers from start to finish. They found that in the earlier layers, performance actually drops. But then, out of nowhere, there is a breakthrough point mid-depth in the network. This is where the model abruptly pieces the characters together, and its spelling accuracy just spikes dramatically.
By zooming in on specific knowledge neurons, the researchers discovered something amazing. The AI uses broad, shared neurons to guess the first letter, but for later letters in a token, it activates highly specialized neurons. The model is dynamically reconstructing the spelling on the fly. It's literally reconstructing reality layer by layer. This proves that for an AI, spelling out a word isn't just pulling from a memory bank. It's a complex learned task that requires intense attention precisely at that mid-layer breakthrough point.
So if the model has to work this hard just to reconstruct a spelling mid-thought, can we fix this blind spot at its architectural root? Instead of relying on expensive chain-of-thought workarounds, researchers are now exploring fundamental changes to how these models are built from the ground up.
Another fascinating study explored this using the percolation model of emergence. While that sounds incredibly technical, it's actually a lot like a eureka moment. By testing AI on 19 synthetic token manipulation tasks, they found that an understanding of character composition doesn't just grow smoothly. Instead, it emerges abruptly, very late in the training process. The AI basically needs to reach a massive critical mass of data before it suddenly gets how letters make up tokens, which is very similar to how these models gradually learn basic common sense.
So the crucial point is how to give the model this knowledge without completely breaking its efficiency. Researchers propose an experimental fix called block causal cross-attention. It's a lightweight modification that essentially feeds the individual character-level information to the model right alongside the subword tokens. This is basically the holy grail because it finally allows the AI to see the individual letters without losing the incredible processing speed that tokenization provides.
We've seen today that the strawberry problem isn't just a funny internet glitch. It's a profound window into the alien architecture of large language models. They are probabilistic engines operating on compressed mathematical tokens, dynamically reconstructing reality layer by layer. Which leaves us with a final, provocative thought to chew on. Since AI fundamentally perceives the world through these tokens, should we really expect it to think like humans at all? Thanks for joining me on this explainer, and keep questioning what you see.